So what we're going to be looking at today are chapters 4 and 5 in your textbook. And these are the chapters having to do with microscopy and also with some spectroscopic techniques. Now I'm going to say one final thing about the exam, and then that will conclude this lecture entirely. And that is that your exam is going to have 33 questions, 25 of which are coming from directly from the book, and the other 8 from this lecture. Now there's going to be nothing on polarization, which is in chapter 4, so you don't really need to look at equations 4.5 or 4.6 on page 93. There's one question having to do with Snell's law, and the other things in there will come also from chapter 5, covering IR, Raman spectroscopy, UV visible, mass spectrometry, which we talked a little bit about today, and there's really nothing on atomic absorption or atomic emission. Now, the section on microscopy is very well written and complete, but there's one thing that I found that was noticeably lacking or was missing from the book, and I checked in later chapters and I didn't really see it in there. Maybe I just missed it, but it's certainly not here where I think it belongs, and that is at least a little bit of discussion having to do with electron microscopy, because you sort of get the impression that electron microscopy does not figure in at all in forensic analysis, and that's just not true. Most of you, I'm sure, are aware that the electron microscope is capable of looking at much finer detail than you could possibly get with an optical microscope. So we've seen in the book already, we can look, magnification without resolution is really useless. So even if we could take 2 lenses or a series of lenses, each one multiplying the image 10 times, and we did that 4 or 5 times or 6 times, and we got up to something that magnified 1,000,000 times, all we would really have would be a blurry image. And you know from reading the book that you can calculate the resolution of a microscope just by using this formula, where the resolution D is equal to lambda, which is the wavelength, divided by 2 times the numerical aperture. And you also see that the numerical aperture is equal to n, a small n that is, which is the refractive index, times sine of theta, or I think your book uses sine of A, which is the angle. If you look at the lens, and then you look at the microscope stage, and this is what you're focusing on, and it would be the angle that's formed. It's actually this half angle here. So if you look at from one end, if you draw a line from one end of the lens to the other end of the lens down to the stage, this angle, both of these angles are the same. I call that alpha, and that's n sine alpha. So there's a couple of things that that you need to know, and one of them is that if you want to get an image using standard kinds of microscopes, what you'll find is that the effective magnification that you can get from one of these things, because of the resolution problems, is somewhere between about 1,000 and maybe 1,500 diameters maximum. You can't really go beyond that because you don't get a useful image anymore. You could put 2 lenses together that would magnify 5,000 times, but you basically would get a blurry image. You wouldn't really get any detail out of it. So, and you can kind of figure this out just very, very simply by putting in lambda the wavelength of, let's choose something like green light, which is 500 nanometers. And that's 500 times 10 to the minus 9th meters. For those of you that are not familiar with the designation nano, it's 10 to the minus 9th. And the numerical aperture of the most powerful lens that you get on a standard microscope is, it's actually called the oil immersion lens. And that's because the lens itself and the stage are actually focusing, instead of in air, which has a refractive index of 1, you have a liquid drop here, which this whole thing is under that liquid drop. And that drop, within that drop, the refractive index of what is called immersion oil, which is what you put on the slide, you're actually focusing within the drop. And that has a refractive index of about 1.52. So it turns out that you can actually get a numerical aperture on that lens that corresponds to about 1.25, and twice that would be 2.5, and if you do that, divide that out, you'll get 200 nanometers. 200 times 10 to the minus 9th, which is actually 2.0 times 10 to the minus 7th, and that's a tenth of a micron, 1/10 millionth of a meter. That is, that you can actually separate two objects that are that close together. Now, if you use so the difficulty is you've got two things you have to deal with here. One of them is the numerical aperture, the other one is the wavelength. And if you realize that the wavelength of visible light is limited by two things. One of them is that the eye is most sensitive to green light around this wavelength. And if you go to a shorter wavelength, down to the blue, you want to make D as small as possible. So you want to minimize lambda, and you'd like to maximize the numerical aperture. Well, we can't do anything with the numerical aperture. We've seen this is the limit, but we can make lambda smaller and smaller, but we can only bring it down to about 400 nanometers, because if we go anything below that, then we're actually going to be into the ultraviolet. We can't see it anymore. Now, we could build special scopes, and there are such things that would enable us to actually get an image. If we were focusing with UV light, you could actually have some kind of a photodetector there that would produce an image. But you're still not going to get much more resolution out of that. So the thing is, you need something that's a lot smaller. And back in the 1930s, it was found that you could actually use electrons. You can't focus an electron using a lens, at least not an optical lens, but you can use a magnetic lens to focus an electron beam. And it's possible to focus an electron beam through a sample. In the past years, the sample had to be specially prepared. It had to be specially dried. It had to be coated with a thin layer of gold or some other conductive material to dissipate electrical charge on the surface. With modern types of electron microscopy, that's no longer necessary. So sample preparation is a lot easier now. But it turns out that if you want to look at electrons, and you still need a wavelength here. And you think about an electron, and you say, well, wait, an electron it has mass. It's a particle. It's not really a wave. How do you actually calculate its wavelength? And it turns out you can calculate a wavelength. There's something called the de Broglie wavelength, which is actually not that difficult to calculate. And I'm not going to really go through the calculation. But it turns out that electrons, depending on their speed, will have wavelengths that correspond to perhaps something on the order of, depending on how fast they're going, it could be somewhere between about maybe 0.1 and 1.2 nanometers. So considerably smaller by maybe up to 3 orders of magnitude smaller than what you would get with visible light. So even beyond 3 orders of magnitude, almost 4 orders of magnitude, I would say. So we're looking at probably, just based on wavelength alone, you'd expect to be able to get something that would be about 5,000 times the resolution that you would get from an optical microscope. And as I already said, you can get about 1,500 diameter magnification, so that would give you about 7.5 million. You get about 7.5 million magnification with that, if everything else was equal. But it turns out that even though with conventional light microscopes, as you go to smaller and smaller sizes, you actually get to you actually are bringing the lens down closer and closer, which is making the angle bigger and larger. So every time you go down, you're actually increasing the numerical aperture. Well, for electron microscopy, that's no longer true, and actually you start to decrease the numerical aperture. So the numerical aperture becomes smaller. So in actuality, the best electron microscopes are maybe somewhere around, probably not even this high, but perhaps we can get up to about 1.5 million magnification on these things. And it depends on what kind of electron microscope we're using, but it'll be somewhere between maybe a couple 100,000, although you can even go down to a magnification of, say, 10 diameters. You're just not going to be, you're going to be looking at a much larger surface, but you'll still get a lot more detail than you would if you were using conventional microscopy. So what are the advantages of it? Obviously, you can look at much smaller samples for forensic analysis. You can look at much smaller samples with greater resolution. And the other thing that you can do, which I didn't mention, which I want to talk about now, is something that you can do with a scanning electron microscope. And that is, if you take a scanning electron microscope, which actually, instead of focusing the beam on a narrow section, what it actually does is it rasters the beam. That means the beam goes back and forth across the area that you're looking at, and it will do that very, very rapidly. It's kind of the way the old TV screens used to work, where the image was, even though you saw it as a single image, in fact, what was happening, it was scanning maybe 60 times a second. It was actually scanning very rapidly back and forth across the screen to give you that particular image. So it's the same thing with electron microscopy. But one of the neat things that you can do with a scanning electron microscope, and that's X-ray fluorescence. So it turns out that if you have, I'm going to use the old model of the atom, the Bohr model of the atom. So you've got a nucleus here, and then you have shells. And in the old way of numbering things, the first shell was called the K shell, and then there was the L shell, and the M, N, O, P, Q, goes up to Q, I think. That's the outermost shell of the largest atoms. It turns out that if you've got electrons in some of these inner orbitals, doesn't matter where they happen to be, and we've got a bunch of electrons in these orbitals here. If you have an electron beam that is actually coming into here, and it hits one of those electrons, which it will do if you're bombarding it continuously with electrons, what will wind up happening is when an electron comes in here and it actually collides with this electron, if it's sufficiently energetic, it will actually knock this electron right out of the orbital. So there will actually be a hole here instead of an electron. Well, what happens then is that one of the electrons in the orbital that is immediately higher than that will actually fall down into that hole. It will actually fall right into the hole there. And when it does so, when it drops down, it's going to lose energy. And that energy happens to be in the region of X-ray radiation. So what it does is it actually emits an X-ray. And you can detect that X-ray, and the scanning electron microscopes that are equipped this way are actually equipped to detect the X-ray, to actually read the energy of that X-ray and produce a spectrum of the energies of all the X-rays. And these things are very well, they're all quantized, which means that you don't get just random energies. They're specific energies for specific elements. So what we're able to do now with the electron microscope is actually perform an elemental analysis on not only on the entire sample, but on a very, very small section of a sample. So if we want to find out what metals, for instance, or it doesn't have to be metals, it could be any elements, are actually in that sample, by focusing on one narrow area, we can actually get the X-ray fluorescence spectrum of that particular sample, and that will tell us the chemical composition. So in addition to being able to look, for instance, at striations, which we can do on a bullet, let's say, and try to match those striations with a gun barrel, you could actually now look at the chemical composition of a bullet at that particular point and check that against the chemical composition of the gun barrel. So you've got a much more powerful tool to use in that regard. Okay, the next topic I'd like to talk about has to do with mass spectrometry, which is a section that is covered in your book. But one of the things that's not really covered is some of the theory of actually what is actually happening in the mass spectrometer. So you know from reading the book that electrons are impinging on various molecules that have been injected into a chamber, a high vacuum chamber, and but the book doesn't really tell you. It just tells you that these molecules will ionize. So I wanted to talk a little bit about the theory of mass spectrometry and actually how this works. So your book does tell you how ions are produced and how they're collected, and it talks about various kinds of ionization, chemical ionization, electron impact. There are other things that are mentioned in there as well. It talks about different ways of actually detecting the ions, but what it doesn't really tell you, or it really doesn't explain, is which I'd like to do with a simple example, is to show you what actually takes place when an electron impacts a particular molecule. And actually, I want to change my pen. I don't think it's dark enough for you to be able to see this very well. So I'm going to go over this again, because I want to focus really on this bond between the two carbon atoms. You also have the hydrogen atoms, so each hydrogen is also sharing a pair of electrons with the carbon atom. Carbon has 4 bonding electrons in it. Now let's assume that one of these high energy electrons comes in here. Now, in the last section I was talking to you about X-ray production. The energy of these electrons is not the same as the energy of the electrons that are in the electron microscope, which are sufficient to eject electrons from inner shells. All this is doing is it's actually ejecting electrons from the outermost shell, which is called the valence shell. So this is a weaker energy beam, but what it does is, as I say, there are a pair of electrons here. There are 2 electrons. One of those electrons is knocked out, and that leaves us with something that looks like this. I'm just going to write this actually as CH3 here, instead of drawing these bonds out, because we're not really interested in anything except what happens with these 2 bonds. So now what we've got is a single electron here, and because we've lost the other electron, we actually have a positive charge. Now this particular species, which is actually usually written like this, would be written like this, because we don't really know exactly how this is localized, so it's usually written like this. So it's written as plus and then a dot, and this is known as a radical cation. Now, the radical part is the dot, that's the free electron. The cation is the positively charged part. Radical cations are very, very unstable, but this is what you actually are looking for when you're trying to find the molecular mass of a particular compound. So let's say I'm injecting a drug, something like cocaine, into the mass spectrometer, because I've got a sample of cocaine. We just busted a bunch of drug dealers, and we've got a sample of what we presume to be cocaine, and we want to actually look at the mass spectrum of the cocaine. So we inject it into the mass spectrometer. We want there to at least be, if we can do this without breaking the entire molecule apart, we want to have at least some of what we call the parent ion, or the molecular mass ion. That's the ion of highest mass that we're going to find in there. So initially we form what's called a radical cation, and the radical cation then normally breaks apart. This kind of radical cation would break apart into a methyl radical, which is the CH3 radical, and then a CH3 plus, which is the cation. So it would break apart into a methyl free radical and a methyl cation. There's also the possibility that we could actually form a radical cation by breaking apart one of these carbon to hydrogen bonds, and that's also likely to happen. We'd also see that as well. And so when that happens, when we break apart one of these bonds here, we're going to get a radical. Well, there's 2 possibilities now. We have the C2H5, which is the ethyl part of this thing, and then we have the H part. So it could either break apart as a C2H5 plus and a hydrogen radical, which is actually a hydrogen atom, or it could also break apart as a C2H5 radical and a hydrogen atom. I'm sorry, a hydrogen ion. A hydrogen, it's actually a proton now. Well, it turns out that because of the way that the mass spectrometer works, we only can see the positively charged ions. And what we actually measure in a mass spectrometer is the ratio of the mass to the charge. So most ions that you get are singly charged ions. So if you see something like that, the mass to charge, the charge is 1. It's a single charge, so we don't really have to worry about it. But sometimes we may doubly ionize something, and then we're going to get something that's going to come, if we look at the mass, at a mass spectrum, we're going to have masses that are going to go from 0 up to whatever the highest measured mass happens to be. And we're going to see, we'll see various masses in here, and the masses will appear as single peaks. So in fact, if we had doubly charged something like this, which actually has a mass to charge ratio, M to Q, that's mass to charge ratio of 30, if it's singly charged, if it's singly charged, if there were two charges, if we actually formed a double radical cation, it's an unlikely event, but we would have two charges in there, then we would get a peak at 30, but we'd also see a peak at 15. Well, there's other ways you can get a peak at 15. You can also just break off one piece of this, and you'd still get a peak at 15. So that's not really a great example of this, but imagine something that actually has a an odd rather than an even mass number, and there are a number of compounds like that that have even mass numbers. Then you could see something, let's say this thing came out, it wasn't 30, we had a molecule that wasn't, let's say, 30 or 40 or something like that, but it was some odd number. Let's say it was 47, then what we would see if that were doubly charged, we would actually see something at 23.5. And if you see something that's at a half, if you're getting unit resolution and you see something that's at a half unit, you realize that that must be a doubly charged ion, because this thing is actually reading entire, we don't get fractional masses. You know, like you see, for instance, when you're dealing with atoms that have masses that are actually not whole numbers. You know, something like oxygen is very, very close to a whole number. It's 15.9994, something like that. So we say oxygen is 16. But there are other elements that have fractional numbers, and that's because those elements exist in nature as a series of isotopes. That is, these are elements that exist where the number of protons are the same. That's what makes it that particular element, but the number of neutrons may be different. And one example that we'll see, which is very important in mass spectrometry, is actually bromine. So when bromine, for instance, is in a sample, and it's something that you see frequently in mass spectrometry, you'll see bromine. You'll see peaks every time you see a fragment, either the whole molecule or a fragment of the molecule that contains one bromine atom. You're going to get a peak, whatever that happens to be. Let's say we had a bromine over here, for instance. And that is now a compound called ethyl. This is ethyl bromide. So this could break up in a number of different ways, and I'm not going to go into all the different ways that this could fragment. But let's say one of the fragments that we had was this piece right here, CH2 with the positive charge on it, and Br. Well, it turns out that bromine has an atomic mass of 79, carbon has an atomic mass of 12, and hydrogen, each one of those is 1, so that's 2. We add those up, we get 13, we get 93. So that's a mass of 93. Well, if this were 93 over here in our mass spectrum, once we collected all the ions, we would see a peak of a particular height here at 93. We would then see another peak at 95 mass to charge units. We'd see another peak right here. So that's 2 units greater than that. And the reason for that is because we've got carbon 12, hydrogen 1, bromine 79. We also have bromine 81, another isotope of bromine. Now it turns out bromine is an unusual element in that it's got 2 isotopes which are almost equal in their natural abundance. That's why bromine actually has an atomic mass. If you look it up on the periodic table, it's something like 79.903. There is no mass that's actually at 80, which is what this is closest to. There's a mass at 79 and another one at 81. There's a little bit more of the 79 mass, slightly more than there is the 81 mass, which is why it has the unit of 79.903 and not exactly 80, which it would be if it were a 50-50 mixture. But the point is that just knowing that and seeing a series of peaks, whatever they happen to be, that are 2 units apart, is telling us that we have a sample that has 1 bromine in it. If there were 2 bromines, this we would actually see another peak here. We might see another peak here that was actually, this peak would be bigger, and we might see another smaller peak here for the possibility where we had a mixture of, where we had, well, yeah, we could actually get mixtures now. We could get one thing where if there were 2 bromines in there, we could have 1 bromine 79 and a bromine 81. We could have 2 bromine 81s and 2 79s, so we get a series of peaks. But by looking at that, that would actually give us some indication of the number of bromines before we did even any other kind of an analysis. So that's what's kind of interesting about this particular technique. There's one other thing that I'd like to tell you about here. Another simple rule that is very good for nuclear magnetic, for mass spectrometry, and that is something called the nitrogen rule. And this rule states that if you've got an organic molecule that contains an odd number of nitrogens, that it's got 1 nitrogen or 3 nitrogens or 5 nitrogens, etc., you're going to get an odd molecular weight. And if you have an organic molecule that contains an even number of nitrogens, or no nitrogens at all, which was still considered to be an even number, you will get a molecular weight that is going to be even. And there are a couple exceptions to this, but I can't think of any exceptions that are actually organic molecules. The exceptions that I'm thinking of are things like nitrogen oxide, nitrogen monoxide, NO, and NO2, both of which have only 1 nitrogen, and you'd expect them to have, based on the nitrogen rule, you would expect them to have odd, because there's a single nitrogen in there, you'd expect them to have odd masses, but in fact this has a mass of 40, 16, and 14, and this has a mass of 32 and 14, which is 46. So those are even masses. But other kinds of organic compounds, like this is a molecule of something called pyridine. This is a chemist's shorthand way of writing this. These are all carbon atoms with hydrogens on them. But if you actually count up all the atoms here, I'm sorry, that's a hydrogen, and another hydrogen here. And these are all, as I say, are carbon atoms here, carbon, carbon, and carbon. You've got 5 carbon atoms, C5, you have 5 hydrogens, H5, and 1 nitrogen. And again, using the nitrogen rule, we'd expect this to have an odd molecular weight. And in fact, we would get a molecular mass that is the so-called parent ion at mass to charge. If we looked at that, 60, 12 times 5 is 60, plus 5 for the hydrogen, that's 65, and 14 for the nitrogen is at 65, that's 79. So it is an odd, it does have an odd molecular mass. One other little trick that you see a lot in mass spectrometry is if you see a peak at 77, peak at 91, mass to charge 91, this usually represents a compound that actually had in it what we call a benzyl group, which is a phenyl, a C6H5. This is the C6H5, 6 carbons and 5 hydrogens in a ring. And then over here, there's a CH2 with a positive charge. Now, when this ion actually is, for instance, you might start out with a compound like this, which is called benzyl bromide. And if you were actually analyzing benzyl bromide, remember you'd get the C6H5, the CH2, that's C7H7, C7H7, so that's your 91, plus the bromine, that's another 79, so this would be 170, that's the parent ion for this, would be, another shorthand way of writing that is just with the Greek letter phi, which is short for phenyl, 5CH2Br, and we would show that radical cation as having a mass to charge of, what did I say, 170. So when the bromine is eliminated, we might see this fragment right here. But what it actually is not a benzyl fragment. It rearranges to a 7-membered ring. So instead of the 6-membered ring, instead of the ring with 6 carbon atoms, this carbon atom is actually absorbed into the ring. And let's see if I can draw this out. So these are alternating single and double bonds. The double bonds are the sharing of 2 pairs of electrons to form that bond. And up here we have a single hydrogen atom. There's a single hydrogen atom on each one of these carbons. So that's C7. That should give us C7H7 if we actually look at that. C7H7, and then there's a positive charge here. That's what makes the ion. So this thing is not called a benzyl anymore. It's now called a tropylium ion. And the tropylium ion is, whenever you see that, it's indicative of this phenyl group. The other thing that you'll see, for instance, if you're looking at something like a hydrocarbon, which is just a long chain arrangement of carbon atoms in a chain. If you're looking at something like an aliphatic hydrocarbon, not something like the phenyl or benzyl groups that I showed you that are actually in a ring, and we call those aromatic. An aliphatic one would be just a chain like CH3, CH2, CH2. We could have a long chain of these things, something like that. In the in mass spectrometry, what will happen is we'll form the parent ion, the molecular ion. In this case, this is butane. That's C4H10, C4H10. And if we lost an electron, that would form the radical cation that would actually be at mass to charge 48 and 10, 58. Mass to charge 58. And then what we would see is what we call fragmentation. And this is what actually produces the spectrum, the fragmentation pattern. So I chose a molecule like this because it's got a very, very simple fragmentation pattern. It will first lose the methyl group on the end here to give you this. As I said before, you'll actually get two things here. You'll get this fragment because you're going to form a radical cation, let's say at this point right here. So you can get a propyl cation and a methyl radical, or you can get a methyl cation and a propyl radical. But either way, what you're going to see is both of these things are actually going to occur. So you're going to see a CH3 plus, which is the methyl cation, and you're also going to see a CH3, CH2, CH2 plus, which is the propyl cation. So when you actually look at the mass spectrum of this compound, you'll see something at what did we say, 58, and then you'll see another peak that'll be over here at 58 minus 15. That's 12 and 3 is 15. So 58 minus 15 is 43. So you see a peak at 58, and you'll see another one at 43, and then you'll start to see peaks that represent the loss of successive CH2 units. So then we'll lose 14, and we'll get a peak at 29, and then we would lose another 14, and we would get a peak at 15. And that actually is the methyl, it's the other thing here. And these will be different heights. But the point is that by looking at the spectrum, the spectrum, the way that these things break apart, that gives a chemist some indication, that gives the forensic analyst some indication of the molecule that he or she happens to be dealing with. And that's what the whole point of this is all about. So we can use, so mass spectrometry is a very, very powerful tool. I've taught you or showed you just a few examples of this. I took a course in mass spectrometry that lasted most of an entire year. So obviously I can't expect you to really learn all the theory and everything that goes into this in a very short period of time. Now fortunately for mass spectrometrists today, most mass spectrometers have built into them enormous libraries that actually have the mass spectra stored in there of maybe hundreds of thousands of different known chemical compounds. Well, it turns out, and we're going to see later on when we talk about things like designer drugs, people would make drugs, would take drugs that were on a controlled substance list and change the structure a little bit to make a new kind of drug, and then that would be something that wouldn't show up in the library. So you're always going to find compounds that are new compounds, things that are not known. And as a practicing organic chemist, someone who spent 30 years in the lab, I had to make compounds that had never been synthesized before. So we had to try to figure out, knowing the rules involved in mass spectrometry, actually how these things, we could certainly look for the parent ions, the molecular ions, but using the fragmentation pattern, that's how we actually determine what it was that we had. And fragmentation patterns can be very, very complex. There can be multiple types of fragmentations that are going on. So it's not that you can necessarily follow from here to here to here to here. There might be some other fragmentation that's occurring, and you'll get, not in this molecule, but in other molecules, you'll be getting multiple kinds of fragmentations that are taking place. And it's kind of, I would liken it to taking maybe one of these 500-piece jigsaw puzzles and dumping it out of the box, and then you've got all these pieces, and you basically have to try to fit them back together to get the original structure. But the pieces don't always fit in the ways that you would necessarily expect them to. It's a lot more difficult than reassembling a jigsaw puzzle. So anyway, that really concludes what I have to say about mass spectrometry, but it is a very powerful tool. The concluding portion of this lecture concerns something that actually isn't covered at all anywhere in your textbook, but it actually belongs right here, and that's nuclear magnetic resonance spectrometry, which is one of the most important tools that an organic chemist or someone who's doing forensic chemistry can possibly be using. So I want to give you at least a little bit of the theory of NMR, how it works, and you'll remember, from those of you that have taken chemistry will remember that electrons have what is called a spin quantum number. This is also true of particles like protons. So electrons can have a spin of +1/2 or -1/2, and the same is true of protons. They can be spinning, all spinning in one direction, all spinning in the opposite direction. If we use this to indicate this is a proton right here, and here is a magnetic field that this proton is actually spinning in. The field is designated as H0. And if I take that applied field and then I inject into that another field that is actually going in a perpendicular direction, what I'm going to have initially is I'm going to have protons, some of which are spinning parallel with the field. We'll call those spin up, and the ones that are anti-parallel are spin down. And they're almost equal. One of them is at the one that's going anti-parallel with the field is at a slightly higher energy. And so what we do is, by injecting energy into here, we can get this this energy to be absorbed. But it's absorbed in a particular way, and I want to demonstrate this to you using this little toy many of you might be familiar with. And what I'm going to do is I'm going to pull this to start my gyroscope spinning, and then I'm going to put the gyroscope down onto this little stand, and you'll notice that it actually balances on the stand. It's spinning at a very, very rapid rate, but I want you to notice the top of it. You'll notice as this starts to slow down, the top of this gyroscope is going to begin to wobble. So it's beginning to slow right now to start that wobble. So you can see right now it's starting to wobble. There it goes. You can see how it's still spinning, but it's wobbling very slowly. 1, 2, 3, 4, 5 wobbles in that period of time that I was counting it, but it was spinning much more rapidly than that. The wobbling is actually called the precessional frequency. So although this is spinning very, very rapidly on its spin axis, its precessional axis, which is going like that, it's going at a slower rate of spin, and that is what we call the precessional frequency. When we actually take this H1 frequency, and if we're sweeping this over the entire magnetic scale that we're looking at right here, we're sweeping through this entire scale, we can actually get these things to match. We can actually get H1 to match the precessional frequency of each one of these particular protons or hydrogen atoms that are in here. Now, if all hydrogen atoms all had the same precessional frequency, then all we would get would be something that looked like that. We'd get a big blob. We wouldn't get any information out of it. But it turns out that each one of these different kinds of hydrogen atoms has a different precessional frequency. And when these two frequencies match one another, that energy is absorbed. We say it's in resonance. That's where the term nuclear magnetic resonance comes from. It's in resonance with the precessional frequency. Energy is going to be absorbed. That produces the signal. Now there's two parts to the signal that I want you to be aware of. One of them is the position on this scale where the signal occurs. Now it turns out in the older instruments, what was done, the instruments that were used back in the like in the 1970s, which is when I really started using these a lot, what they did was they actually swept the entire frequency. So they would hit one proton, then another proton, then another proton, by changing the frequency of the magnetic field of the oscillator coil. So what was done later, which was actually made the process a lot better and a lot faster, was a pulse. A pulse was applied that actually excited all of these things simultaneously. And that produced a very strange looking spectrum called a free induction decay. And the way a free induction decay might look would be you'd get a very, very large thing, and then it would get smaller and smaller and smaller and smaller until it would decay away to nothing. And there might be other information in here, so it wouldn't be like straight lines, but there'd be little peaks superimposed on these peaks as well. So you'd see something that maybe looked like that, and this is called a time domain spectrum. T-I-M-E, domain spectrum. Now a time domain spectrum is basically useless. This is the time scale from 0 to some number of seconds out here, and we call this ringing, and this actually rings down to nothing. But when you, so I said that you really don't get any information from the time domain. What you really want is something called a frequency domain spectrum. And the way to convert from time domain to frequency domain is to apply a mathematical operation called Fourier transformation. Now you've seen this term already in your book because there's a section in your book called FTIR, which is Fourier transform infrared spectroscopy. So this is a Fourier transformation, and it involves some fairly sophisticated calculus that I'm not going to go into. But the machines do this automatically. They take the time domain spectrum and they generate out of that from the Fourier transformation a frequency domain spectrum. And I have an example of a frequency domain spectrum right above this. And this is something that is useful for a chemist, because we can look at this and we can figure out from this spectrum what we're actually dealing with here. So, all right, so I want to talk a little bit about how we get information out of the frequency domain, or the Fourier transformed spectrum. This is, I said, what you would actually see on your computer screen if you were taking an NMR or on your printout. It would look something like that. So what we see here are three separate signals. You'll notice that there's a scale here which is in what we call ppm, or parts per million. And you don't really need to worry about what that is, but it refers to actually the position on that entire frequency scale where these things actually appear. And the 0 of this is with respect to an internal standard that is always put into the system, which is something called tetramethylsilane. It's a silicon atom with 3 methyl groups, 4 methyl groups attached to it, and it happens to have your machine, your instrument is actually tuned so that this appears at 0. So that's the standard position. So when we say that this is, for instance, this peak here is centered somewhere around maybe 1.2 or 1.3 parts per million, it's with respect to tetramethylsilane. That's the position. So we call the position the chemical shift. And the chemical shift is important because it tells us something about the chemical environment in which that particular hydrogen atom finds itself. That is, what is that hydrogen atom attached to, and what other groups might be nearby the atom that hydrogen atom is attached to. So that's the information that we hope to be able to get out of this. So this is the TMS peak, the tetramethylsilane peak. We're not going to really worry about that peak. and then we've got 3 other peaks. And each one of these represents a different kind of hydrogen atom. So I'm going to start with the peak that's over here at somewhere around maybe 2.7 parts per million. And you'll notice that this peak actually appears as it's actually what we call a doublet. The tetramethylsilane peak is a singlet. All of these hydrogens are equivalent. Each one of them is equivalent to every other hydrogen, and this just appears as a single peak. So that's a singlet. This is what we call a doublet. And the position of the peak tells me something else. The chemical shift tells me something else, that's likely going to be a hydrogen atom that's attached to an oxygen atom, what we call an alcohol. So that's the first piece of information that I get from looking at this. And then the combination of this is a doublet. And then you'll notice that we also have a triplet over here. And over here we have a quartet. And this combination of a triplet and a quartet is also indicative of something. And I'll explain in a second what I mean by that. Because this we refer to as multiplicity. That is, how many parts does this peak actually have? So the multiplicity here is, this is a quartet, that's a doublet, and that's a triplet. That is, this has a multiplicity of 4, this is 2, and that's 3. And that's very important. And multiplicity, the way that we actually define multiplicity is we look at whatever the hydrogen atom is attached to, there's going to be another atom attached to that, and then that atom will have either one or more hydrogens attached to it as well. So if this, for instance, was a carbon atom and it had 3 hydrogens on it, all 3 of those hydrogens would be equivalent to one another. This hydrogen atom would see 3 hydrogen atoms adjacent to it, and these 3 hydrogen atoms, all equivalent to one another, would see 1 hydrogen atom adjacent to them. What these hydrogen atoms see, the multiplicity is going to be equal to the number of hydrogen atoms that they see plus 1. So the number that they see, we'll call that n plus 1. So you can see that whatever is on this carbon atom here, let's say there were 3 hydrogen atoms, all equivalent. Each one of those sees 1 hydrogen atom plus 1. And the reason for that is because if there are only 2 atoms in there, they're either going to be spin up or spin down. So those are the 2 possibilities. So it sees what we call a doublet. Now on the other hand, the hydrogen, I want to actually make this not methyl alcohol, but I want to extend this a little bit further. So I'm going to erase this here, and then I'm going to put a carbon atom, and I'm going to put 2 hydrogens here, and then I'm going to put another carbon atom with 3 hydrogens on it. Because one of the things that I know from looking at the spectrum, wherever I have a triplet and a quartet, that is indicative of what we call an ethyl group. That is a methylene, a CH2 plus a CH3 adjacent to it. So it's C2H5, that is an ethyl group. And the way this works is, if we actually look at the spectrum again, now we can see, I've already talked about each one of these hydrogen atoms being equivalent to one another. They're going to see the doublet over here for this. But this hydrogen here is going to see 2 plus 1, so it will see a triplet. This CH2 here, it sees the doublet, but over here it also sees 3 hydrogen atoms plus 1, which is the quartet over here. So this is the methyl group. This is the this signal comes from here. The doublet comes from the OH group. We've already said that, and the triplet comes from the CH2 group here. And we also, when we run these spectra, we also get an integration, which tells us the relative number of protons in here. So this would actually integrate. If we ran the integration, we would see this would come out as 2 units, this would be 1 unit, and then this would be 3 units. So we get the idea that it's 2, I'm sorry, 3, I didn't do that correctly. It's 3 for the quartet. The methyl group, I'm sorry, I've kind of messed this up. The methyl group is going to be, no, I've shown that right. The methyl group is over here. That's the triplet, and this is the quartet. So the quartet is 2, so it's going to be 2 to 1 to 3. That's the ratio, 2 to 1 to 3. The peak heights of those things are going to be 2 to 1 to 3. But the other information that we can get out of here actually has to do with determining whether or not, for instance, if we look at this thing, this is getting a little, board's getting a little complicated. Of these peak heights, not just the overall intensity from here to here to here, but looking at within each group. This one here, the quartet, the doublet, and the triplet. What we're going to see is that this is, each of these is going to be 1 to 1. That is, the heights will be the same. This one here is going to be 1 to 2 to 1. And this is going to be 1 to 3 to 3 to 1. And if we had a pentuplet, which is 5 peaks, that would be 1 to 4 to 6 to 4 to 1. Now, if you're really a good mathematician and very astute, you start to recognize that there's a pattern here. And this is what is called Pascal's triangles. So if you've actually ever constructed Pascal's triangles, it looks sort of like this. You get 1 to 2 to 1, 1 to 3 to 3 to 1, 1 to 4 to 6 to 4 to 1, and then it would go 1 to 5 to 10 to 10 to 5 to 1. And that actually is showing you the multiplicity that you get. This is a doublet. Here's your triplet. And here's your quartet, the 1 to 3 to 3 to 1. And the way that these things come about, I'm just going to look at the triplet as a simple example, the 1 to 2 to 1. The reason that you get that is because you have to look at the actual spin states. So the triplet, remember, is from 2 protons. So what are the arrangements in spins that 2 protons can have? Well, they can both be spin up, they can both be spin down, or one of them can be spin up and spin down, or they could also be, this one could be down and that one could be up. Well, these two are actually equivalent. This is different and that's different. So this is 1, there's 2 of these, 2, and there's 1. And if you did the extension, you'd see if you did that for 3 protons, you'd get the 1 to 3 to 3 to 1, etc. So what we're actually getting out of all of this is a pattern that is very, very useful. We use both the what we call the multiplicity here. That's the number of peaks that we get, the multiplicity, plus the chemical shift. And also we look at what are known as coupling constants. These things can be further split. For instance, this one right here, let's see, this one right here that's showing the quartet. The quartet, if you actually looked at it, if you had a powerful enough magnet, you would actually see, using 100 megahertz magnet, which is the low-powered magnets, you'd see, you probably wouldn't be able to see very much information. But if you get up to something like this, the most powerful magnets they have right now, these 900 megahertz or 950 megahertz magnets that are out there, and there's that 1.2 Tesla magnet, I'm sorry, 1.2 gigahertz magnet that's out there, that's going to be built and online in a couple of years. That particular magnet will actually be able to resolve this down to finer and finer structure. So you'll not only see the quartet, but you'll see the quartet will be split so that it's actually going to be a doublet of quartets or a quartet of doublets, depending on how you look at it. And you might even be able to see like 8 peaks in there. So all these things give us information about the nature of the chemical that we're dealing with and enable a forensic scientist to be able to assign a chemical structure. And that's very valuable when you're doing drug analysis, particularly when this is a drug that you might be looking at that has never been synthesized before. Somebody's doing a designer drug, and it's not something that that is available in a library of spectra. So you need to be able to analyze these things to figure that out.